You flip a switch, and instantly the room floods with light. It happens so fast, we rarely stop to think about the physical reality. What exactly is moving through that copper wire in that exact millisecond? That movement is what we call electric current, represented by the letter I. Think of it as a bahav, a flow. It is the sheer volume of electrons passing through a single cross-section of the wire over a specific amount of time. But here is the catch. Electrons are inherently lazy. Left alone, they jiggle around aimlessly. They will not organize and move in a single direction unless an external force acts on them. That force is voltage. It is the electrical pressure, the potential difference, that commands the electrons to move. So if the current is the flow of the water, the voltage is the steepness of the mountain pushing that water downward. You cannot have the flow without the initial push. Curious, which leads to a very logical question. If voltage is constantly pushing these electrons forward, why doesn't the current just keep accelerating? Why doesn't it speed up to infinity? Because the wire itself fights back. As the electrons move, they constantly crash into the atoms of the conductor. This physical opposition is a rukavut built into the material itself. In physics, we call it resistance. Electricity functions as a constant tug-of-war. The voltage pushes the charge forward, and the resistance pulls it back, keeping the flow in check. In the 1820s, a physicist named George Ohm figured out exactly how this tug-of-war works. He realized that jitna bada push, utna bada flow. As long as the temperature stays the same, the current is directly proportional to the voltage. This graph shows the potential difference in current for a nichrome wire, and you can see how perfectly they align. This direct relationship is captured in the formula V equals IR. That R is resistance, and it is the exact mathematical factor controlling how much current you get for a specific voltage. Because the plotted points form a perfectly straight line, we know that the resistance of this specific piece of wire isn't fluctuating. It remains absolutely constant under stable physical conditions. This gives us the power of prediction. If you know the pressure from the battery and the resistance of the wire, you can calculate the exact flow of the current before you even build the circuit. But what exactly determines that resistance? First, it's about physical dimensions, starting with length. A longer wire means the electrons have to survive a longer obstacle course, creating more Rakawa. Resistance is directly proportional to length. Then there is the area of the cross-section. This is an inverse relationship. If you use a thicker wire, you are essentially building a wide multi-lane highway. The electrons have more room to maneuver, which drops the resistance. But you can't build a highway out of just anything. This brings us to resistivity. While resistance changes if you stretch or flatten a wire, resistivity is fixed. It is the internal DNA of the material itself. It is the exact reason copper is born to be a great conductor, while rubber is destined to be an insulator. We choose a material for its unchangeable resistivity DNA, but we cut and shape it to control its absolute resistance in the real world. When we start connecting multiple resistors, we have two options. The first is a series combination. This is connecting things ek ke baad ek, end to end. The exact same current is forced to push its way through every single component in the loop. But there is a fatal flaw here. Ek fail to sub-fail. Because there is only one physical path, if a single bulb blows, the entire circuit is broken. Everything shuts down. To fix this, we use a parallel combination. Instead of one single road, the circuit splits into multiple branches. The current divides, taking alternative paths simultaneously. Yahi hamari ghar ki wiring hoti hai. By wiring a house in parallel, each appliance gets its own independent path. If the TV breaks and that specific path goes dark, the ceiling fan keeps running without a hiccup. Parallel circuits allow us to safely segment and control our electrical maze, keeping the whole system safe from a single isolated point of failure. There is one final piece to this puzzle. When all those electrons are violently crashing into atoms, fighting the rukavat inside the wire, where does all that expended energy actually go? It doesn't just vanish. That constant subatomic collision creates electrical friction, and that friction is released into the environment as heat. This is Joule's law of heating. The heat generated scales exponentially with the current, it scales linearly with the resistance, and it builds up the longer you leave the power running. This conversion of energy into heat is an inevitable physical certainty, dictated by the math of the conductor itself. And instead of seeing this heat as a problem, engineers intentionally design high-resistance materials to weaponize Joule's law for our benefit. When you plug in an electric iron, you are pushing current into a material with massive resistance, generating enough heat to press the wrinkles right out of your clothes. An incandescent bulb uses a tungsten filament because its extreme resistance causes it to get white hot and emit brilliant light without melting away. A safety fuse does exactly the opposite. It uses a specific thin wire designed to melt. If the current spikes to dangerous levels, the intense heat breaks the circuit, stopping the flow before your appliances catch fire. Electricity is not magic. By managing this balance of push, flow, and friction, we transform a simple movement of electrons into the precise light, heat, and mechanical safety we rely on every day.